if that's the case. I'm just taking a moment here to have my screen sharing. Okay, how does that look? Just to confirm, looks good. Okay, great. Well, thanks for that introduction, and thank you to ISPE for having me, and hello to Richard and Neo, my colleagues. I hope everyone is doing well and staying safe in these days recently. Today's webinar is titled Steam Sterilization, Microbiology, and Autoclave Performance Qualification. The introduction really speaks for itself, but I'll add a couple points here about myself. I'm a microbiologist by training, and at Steris, my specific responsibilities are to provide technical support to the industry with educational webinars and presentations around what we call critical environments. So this is use of disinfectants and sanitizers in the clean room, and sterility assurance products. These are the biological and chemical indicators used for confirming sterilization. And then lastly, what we're calling barrier product solutions. These are different wrapping materials that are used to prepare equipment and items to go through the autoclave sterilizer. So really my goal is to stay abreast of the best practices in the industry around these different sterility assurance functions and ideas. So I really invite there to be questions, add them to the chat box. I will try and manage that with a couple different monitors here, but if I don't see the chat during the presentation, be sure that I will address questions at the end of the slides. Here's my contact information. Please take note of this. If after the presentation you have questions that maybe I can help you with, or if you have ideas that were unclear, please reach out to me by email or telephone, and I'll certainly get back to you and we can have a discussion that way as well. That being said, as I mentioned today, we're talking about steam sterilization on a microbial level. This is really a high level presentation overall, but I want to introduce you to these interesting concepts around why microbiology is important with our autoclave performance qualification. So I'll start with an overview of the microbiology. I'll talk about some very fundamental basics of an autoclave design and function, and then move to really the most important part here is the autoclave performance qualification. This is the set of activities that we're performing in order to demonstrate that we have successful sterilization. And then we'll talk about some regulatory expectations. These are global expectations. It's good right now in our industry with regards to autoclave performance. The regulatory expectations have been harmonized by and large. I'll call out some new regulations and some focus points that I feel are being looked at a little bit more during audits and such. And then lastly, to help us with these regulatory expectations and to help meet the performance qualification goals, we'll talk through some validation maintenance best practices. Now, this is not maintenance insofar as we're mechanically working on the autoclaves, but rather maintenance using process verification tools. So this is really the part where we're confirming on a routine basis the performance of the autoclave is as we expect. And since we're on video, I do have some little bit of show and tell, so I'll leave some time at the end here to do a show and tell with these process verification tools. That being said, as promised, we'll start with steam sterilization microbiology. A little history lesson here, just to put things in perspective. The first steam sterilizer, the first autoclave, was invented by a gentleman named Charles Chamberlain in 1879. And here's a drawing of that autoclave 140 years ago. Chamberlain was working in France with a gentleman by the name of Louis Pasteur. He was also a microbiologist, really a founding father of bacteriology or microbiology in Europe at the time. These two were really integral in learning how microorganisms grow, but then fundamentally upon the invention of the autoclave, how microorganisms are killed in a steam sterilization process. So this has been around a long time. The science is not new, and really not much has changed with regards to the science since the late 1800s and early 1900s. And I bring this all up just to transition here. The first AMSCO sterilizer was built in the early 1900s, and AMSCO is now called Steris. So Steris has over 100 years of expertise in sterilization, specifically in steam sterilization. And really that brings us to today to talk about some of these concepts. So to be on the same page, I'd like to start with the definition of sterile. This is really the concept of being free from bacteria or other living microorganisms. This is 100% free of all viable life forms in absolute terms. It's much like a light switch. It's either on or off. There's no in between. So this is fairly simple. There is no kind of sterile or almost sterile. It is or it isn't. The complexity comes in that sterility cannot be absolutely proven, just inferred based on the method and the validation. So that's why these process verification tools or the validation tools like biological indicators are so important, because these are the tools that confirm and demonstrate sterility. So in an autoclave, specifically today, we're talking about steam sterilization, but these concepts apply to all different types of sterilization. And an autoclave function is to eliminate all forms of life, specifically microbial bacterial life. That's our goal, is to kill these microorganisms. However, we do not want to have an adverse impact on the essential properties of the materials being sterilized. And I mentioned that we've learned a lot in really the last 140 years about microorganism death. So we have some models, mathematical models to show now that microbial death is expressed as a log reduction in population. So when we're talking about sterilization, we're really talking about reducing a population of organisms from uh, whatever number in the validation. We're talking about 1 million organisms, reducing that population until we're fairly certain that we have no surviving organisms. So that's the goal here, is to demonstrate a reduction in the population. And likewise, microbial survivor is expressed as a probability. So a probability of a non-sterile unit. This is a common term in our industry. Also a sterility assurance level. These are probabilities to demonstrate to a certain level that we do not have any surviving organisms. So I mentioned that, of course, today we're talking mostly about autoclave or steam sterilization, which is the most common, I would say, form of sterilization in our industry, along with dry heat sterilization. These principles of microbiology, the principles of validation that we're talking about today, are specific to an autoclave, but they do apply to all of these other types of sterilization or modes of sterilization as well. We'll focus on the steam just to give you an example of the different concepts, but when we're validating a sterilization process, it's really the same type of methods throughout. Oh, I see that somebody tried some drawing on my screen there. I think I do want to say that we will share the PDF of this presentation as well afterwards. So if you have um, interest afterwards, take a look at the PDF we'll send out, and you can always contact me or my colleagues Richard and Neo if you have questions. Excuse me, I'm still getting my caffeine this morning. Okay, so Back to the microbiology, what's important here when we're using microorganisms for validation or using it in testing autoclave performance, we need to understand the difference between what's called a vegetative bacteria and a spore-forming bacteria. So I'll use some terms here, but I'm really just trying to make a couple points. So it's not important that we understand all these terms, but just a couple concepts here. Differences between the vegetative and the spore-forming bacteria. Typical gram-negative bacteria like E. coli or Pseudomonas are different. These are the vegetative. They're different than the bacterial endospores like Geobacillus stereothermophilus. Some similarities is that they're all commonly found in our environment, but the vegetative are killed at temperatures as low as 60 degrees Celsius versus the endospores have optimal growth at that temperature. And really, the biggest difference is the resistance to sterilization, so resistance to steam. And that's where we're talking about a term called D-value. D-value is really just a measure of an organism's resistance to different sterilization modes. So for purposes now, I just wanted to point out that the spore-forming organisms like Geobacillus stereothermophilus have an approximate d-value of 2, which is approximately 400 times more resistant to steam than the vegetative cells. So that's why we select organisms, these spore-forming organisms, as our indicator, biological indicator for testing steam sterilization in an autoclave. The concept here is that if we demonstrate that we can kill these resistant bacterial endospore populations in our validation, then any less resistant organisms would be killed as well. What about an endospore is makes it resistant to the mode is really the fact that there's a protective coat formed around the essential properties of the cell. And this is what makes them very resistant to conditions that are typically detrimental to the vegetative cells. However, since 1879, the invention of the autoclave, we've learned a lot about how steam is efficient and effective at killing the endospores while not destroying the materials to be sterilized. And we'll talk really quite a bit about that method of sterilization using steam. And as I mentioned, this is the fundamental properties. This is the fundamental statement about validation and using biological indicators. If the spores are killed, if the biological indicator specifically is killed, there's a high probability that the less resistant vegetative bacteria are killed as well. That's really the most important point with biological indicators. However, we do have an autoclave, which is a great invention, and steam sterilization is very effective and efficient. But what about steam makes it a very good sterilant? Specifically, the energy held within steam is greater than dry air or water. Specifically, saturated steam condensing onto a surface releases the energy essential to kill the possible microorganisms on the surface. So saturated steam is where there's a balance between the pressure and the temperature. You have the maximum possible energy for the sterilization to occur. So having said that, it's important that when we're running an autoclave sterilization that we do not have air present in the chamber. The air can act as an insulator and protect any possible microorganisms from being killed by the steam. So in an autoclave cycle, often there's a robust air removal phase, which is called a pre-vacuum phase in a lot of autoclaves. And that function is to remove all air from the chamber and associated piping. And that is to be sure that this saturated steam contacts all surfaces of the materials to be sterilized. And likewise, the equipment needs to be cleaned prior to the steaming, as any residue or dirt or oils on the surface can block steam contact to these materials. Okay, I introduced the concept of reducing a population of organisms in order to show microbial death. This happens logarithmically. So it's a function of time and temperature. As time increases, temperature can be less, and you will achieve the same level of microbial death. Likewise, if temperature increases, you need less time in order to reduce that microbial population. In the last 100 or so years, we've really developed some mathematical models or assigned some physical properties, math properties to bacterial populations. So concepts like D value and Z value talk about the microorganism resistance to steam, while lethality is a physical measurement that can be used to estimate microbial death as well. Here on the screen, I have the logarithmic curve. This is a population death curve for a biological indicator, and it's a log scale graph. On the left, you have population, and on the right, you have the log population, starting with 1 million individual bacterial endospore cells. Across the x-axis, the bottom, we have a time scale. And this is really just a real example of what a biological indicator curve looks like in a steam sterilization cycle. And I wanted to introduce here again the concept of the d-value resistance. So here at 10,000 or 10 to the fourth power organisms, if the steam cycle of 121 degrees lasts 2 minutes, or every 2 minutes of the cycle, the population will be decreased by 1 log, or from 10,000 to 1,000, 10 to the fourth to 10 to the third. And that 2 minutes in this example is what's called the d-value. Every 2 minutes, the population is reduced by 1 log, or 90%. So some organisms have more higher d-value or a lesser d-value, but for our validation purposes, the biological indicator typically has a d-value around 1.5 or 2 minutes. So that's the definition of d-value. This is very important with regards to the biological indicator. One of the key attributes along with population is the d-value, and this is the time to reduce the population by 1 log. And this, I wanted to point out, I see here I have a reference, PDA, technical report number 1, Parenteral Drug Association. Tech report number 1 is really the guidebook that we're using to help us meet regulations when we're performing autoclave and steam sterilization validation. That's where I got this definition, is from PDA Tech report number 1. Very good reference there. So real quick, typically if we were in person, this would be a quiz question for all of you, but I'll give you the answer, but a time to think about this concept. If you're starting with a biological indicator that has a spore population of 1 million or 10 to the sixth and a D value of 2 minutes, think about how long it would take to reduce that biological indicator population from 1 million to less than 1 possible surviving microorganism. 10 to the sixth with a 2-minute d-value down to less than 1 would take 12 minutes in the cycle at 121 degrees Celsius to reduce the population to less than 1. So this is really the biological indicator example. This is the expectation harmonized throughout the industry when we're using biological indicators to start with a population of 10 to the sixth, approximate d-value of 2, and a cycle that certainly is more robust than 121 degrees for 12 minutes. We want to add that extra time for sterility assurance, but this is the concept where we're coming up with those parameters. And likewise, also taken from PDA technical report number 1, there's this concept of lethality, which is a physical measurement. So we're using time and temperature to assess a cycle's ability to reduce that microorganism population. Lethality is the number of equivalent minutes of steam sterilization at a temperature of 121 degrees. So that's really going back to the biological indicator example. 121 degrees is our base temperature. 12 minutes in a sterilization cycle at 121 would theoretically reduce that population. However, if you had a higher temperature like 123 degrees, it would take less time on the clock to achieve the same microbial kill. So you would have a shorter cycle, presumably. And likewise, if you do not have a cycle that reaches that critical temperature of 121 degrees, you accumulate less lethal kill during that same amount of time. So you would need a longer cycle to kill. Okay, so that's really the fundamental concepts here with regards to steam sterilization as it relates to microorganism kill. We have the biological indicator, the microbiological kill, and now introducing the physical measurement with time and temperature within the autoclave. So one last graphical representation here. Across the bottom x-axis, this is time, and up the y-axis on the left is what we're calling the lethal value, or F sub 0, FO. And you can see at 121 degrees, we're accumulating one lethal value, one FO per minute. So this is a temperature curve. These bars are 1 minute increments showing different temperatures throughout an example sterilization cycle in an autoclave. So you can see here at 121 degrees, the F value is 1, and up at 123 degrees here, your F value is 1.545. So at 123 degrees, you're accumulating a minute and a half lethality per clock time. So this is how we build a robust sterilization cycle, is by having a set point that's a little bit higher than this critical 121 temperature. So that's why you'll see the autoclave cycle set point is typically maybe 121 or 122 degrees for 30 minutes to be sure that that critical temperature is achieved at all locations throughout the autoclave and throughout the equipment in the load. So as I mentioned, factors affecting sterilization and lethality are time and temperature, but also pressure in order to confirm saturated steam. Something that I think is a hot topic right now in our industry with regards to audits and expectations from regulations are how we're controlling the load within the autoclave, because this affects lethality and microbial kill. So how do we have a cycle prepared, the equipment prepared for the cycle? How is it wrapped? What are the materials of construction of the equipment? If it's liquids versus stainless steel or plastic items, all of this needs to be tested during the validation and controlled during day-to-day operations. So this is a hot topic, and we'll touch on that a little bit more as well. So that was a very high level introduction to the microbiology and some of the concepts behind biological indicators, microbial kill, and all of that goes into how Charles Chamberlain in 1879 developed this equipment called an autoclave. So the function, the equipment of an autoclave really has not changed much in the last 100 or so years. We're still using a pressure chamber with saturated steam. The factors that have changed, I would say, are more around how we're controlling the cycle, how we're monitoring and confirming the sterilization cycle. But these autoclave basics really have not changed much. So an overview of how we're using autoclaves today in pharma and biotech industry. This is, again, a high level example. This specific purpose is contamination control to kill the microorganisms like we talked about. This could be sterilization of waste that's known to be contaminated, could be liquid or microbiological media sterilization in a laboratory environment, could be terminal sterilization of your actual drug product to ensure that these drugs are sterile at the time of use. I would say most common is to sterilize components used in aseptic processing of parenteral drugs. So this is the sterile filling in an aseptic manner of our pharmaceuticals. So I have a photo here of some stainless steel filling pumps, and on the right there is some plastic tubing. The product contact surfaces are typically sterilized either in the autoclave or maybe steam in place sterilized at the filling line. But this is probably, I would say, the largest use of the autoclave in our industry. Critical features, again, high level of the autoclave. Sanitary design, we're using clean utilities, whether it's the clean steam or pharmaceutical grade air that's been filtered. Also, the steam qualities, as I mentioned, should be monitored by quality assurance for presence of non-condensable gases, impurities, also for the saturation point. Remember, saturated steam has the highest capacity for microbial kill. That's where you have a balance between the temperature and the pressure. And then finally, to ensure that we don't have any air entered into the system, we need a leak-free design. Cycle parameters are time, temperature, and pressure. Remember, these are also the critical attributes for microbial death. All of this comes together with the physical and the microbiological. As I mentioned, air removal is very important to ensure that steam has the opportunity to contact all surfaces of equipment within the autoclave. Typically, there's two different types of air removal possible. Could be with gravity displacement. This is where air is forced out of the chamber through the drain or steam traps by steam entering the autoclave. This is typically for liquid sterilization. More commonly for our aseptic processing filling parts is the pre-vacuum style autoclave, where air is actively removed via a series of steam injection and vacuum pulses. So this is a very effective and very efficient method of air removal, and we have some process control devices, specifically air removal verification tests like the Bowie-Dick test, that helps us on a daily basis to confirm that we have a successful pre-vacuum pulse. So we talked about the biological indicators to be used during validation. We also have the Bowie-Dick air removal verification test used on a daily basis to help us confirm that our autoclave pre-vacuum pulse results in complete removal of air prior to sterilization. A couple things here with regards to the cycle. This is a very generic or example cycle printout from an autoclave. Across the bottom, you have time. Up the left y-axis, there's temperature, and up the right y-axis, we have pressure. Right here are the pre-vacuum pulses that I mentioned, where you're injecting steam to a specified pressure and then followed by a vacuum. This repetition of steam injection and vacuum ensures there's no air prior to steam injection and heat up to your critical sterilization temperature, where you're holding for the validated sterilization time. So this is really, from a sterility standpoint, the most critical three phases of the cycle. That's why we have biological indicators to confirm sterilization and the Bowie-Dick test to confirm the pre-vacuum pulsing. At the end here, we have drying and cooling just to be sure that our equipment upon removal is safe for use. So I mentioned the equipment loads and the preparation is very important. Part of the validation is to define the loading configuration. This is the allowable materials during a sterilization cycle. So we're challenging during validation all of these different parts and the configuration, possibly defining maximum allowed numbers of equipment or minimum number of equipment, and we're challenging that during the validation. And this is increased expectation here from regulations, how the equipment is prepared for sterilization. It needs to be cleaned, it needs to be wrapped using specific types of materials to show that it can be reproducibly prepared, could be sterilization boxes or special types of bags as well. So we're going to spend a couple minutes now on this equipment preparation with regards to the sterilization wrapping, as it's critical in the validation and the routine procedure and verification. So the biological indicators, the autoclave parameters, but also how we're preparing the equipment for sterilization. So there's a lot that goes into this, and this is a hot topic, but I just am going to pull some best practice recommendations here with regards to the sterilization wrapping. As I mentioned, it's important to show consistency and efficiency during the preparation. Second, we're looking at the material ability to allow steam penetration and aeration during the sterilization. So this is happening within the autoclave. And then during storage and transport, the sterilization wrapping must maintain a good microbial barrier to protect your critical parts here. And then this is sometimes overlooked. The whole purpose of preparing and wrapping prior to sterilization and through sterilization is so that we maintain sterility until the time of use, where we need to aseptically unwrap and present these parts to our filling line. So this last bullet is often overlooked, and yet it is the most important part of the sterilization wrapping. So think about when you're evaluating sterilization wrapping materials, always keep the end goal in mind. Just a quick overview of sterilization wrapping attributes. We need to select materials that do not contribute contamination to the clean room, so materials that do not generate particles. Needs to have a good microbial barrier, not allowing contamination of the sterile items. Often when we're post-sterilization, moving sterile equipment through the clean room, we might need to have 2 layers of wrapping in order to protect those parts. Maybe if you're moving from a grade C environment to a grade A or an ISO 7 to an ISO 5 clean room, you might remove the outer layer of sterilization wrapping to move through the material handling airlocks. So think about possibly double wrapping or compatibility with different surface sanitizers, disinfectants, and sporicides. Again, this is to decontaminate the surfaces of the sterilization wrapping when you're moving the equipment from one clean room to the other. So really the legacy type of sterilization wrapping is this blue paper or cellulose-based wrapping. There's some pouches here on the lower right, but these don't necessarily meet those attributes that I just talked about. So the expectation now in the industry is moving more towards better protection of critical surfaces using polyolefin or Tyvek based sterilization wrapping. So on the left here, you can see that there's some tubing, and within this very small drawstring bag is a stainless steel filling needle. On the right here, we have a stopper bowl And this again is a product contact surface, and it's being covered by an elasticized cover made out of Tyvek. So those primary contact surfaces are first covered with this type of wrapping, and then a secondary cover here on the lower left. You can see in the top bag is a Tyvek and film pouch. The primary product contact is first covered with the drawstring bag, and then secondly in the pouch. On the lower right, that stopper bowl with the elasticized cover is then placed in a drawstring bag, which is tied up and closed for sterilization. So this is really the expectation now versus using the cellulose or paper-based materials. A few of the attributes of the Tyvek-based materials: we have very low particulates during wrapping and unwrapping. We also have a better ergonomic situation for the operators. It's a faster, more reproducible method during wrapping and unwrapping. During the autoclave cycle, again, we're thinking about the improved microbial barrier properties with comparison to cellulose. Also, it's breathable, compatible with steam, and able to tolerate temperatures up to 127 degrees. So these are the attributes during storage, transport, and use that need to be considered: microbial barrier properties, particle generation, compatibility with the disinfectants, and lastly, compatibility with VHP, vaporized hydrogen peroxide decontamination, if you're using a RABS, restricted access barrier system, or an isolator filling line. So this is really the advantages of that Tyvek over the cellulose paper. So take a look at the equipment, how it's being wrapped and prepared, and these different attributes during the process. So all of those considerations, the use of biological indicators, measuring temperatures in the load, controlling the load configuration, including the sterilization wrapping, brings us to the autoclave performance qualification. This is the demonstration that the way we've assembled the load and the cycle that we're using in the autoclave does what it's expected to do. The validation process of an autoclave is really broken down into three different sections: the installation qualification, or IQ, the operational qualification, or OQ, and really what we'll focus on today is the performance qualification, or PQ, which is use of biological indicators, use of temperature measurement or thermocouples, use of chemical indicators to show the actual kill of microorganisms, using the loading pattern, the wrapping methods that we've defined in our cycle development. We're demonstrating that our process results in a sterile product. So the physical performance qualification part of this I mentioned is using thermocouples or temperature measurements, really to demonstrate lethality, the F sub zero, reproducibly over multiple runs. Not only are you showing the temperatures within the sterilizer, but also at the hardest to sterilize locations within the equipment throughout the load. The microbiological, here is where we're using our biological indicators to show that sterility assurance level, or a very low probability of a non-sterile unit at the end of the sterilization cycle. So we're actually, during the validation, using live microorganisms to start, and then demonstrating that they're no longer viable at the end of the cycle. And we're again using these worst case principles where we're placing biological indicators at the hardest to sterilize locations throughout the load. And here are the requirements. It's really fundamental. It's harmonized across the world, whether it's FDA or EMA or Asian regulations or South America. everywhere across the world, we're expected to demonstrate the same performance qualification requirements: the sterility assurance level, the physical PQ with the FO or accumulated lethality, using thermocouples for temperature mapping at these worst case locations. Microbiological performance qualification is using the biological indicator, which is the worst case organism and population and resistance to steam. So I have a few examples here with regards to these expectations. The sterility assurance level I mentioned is at least 10 to the minus 6 demonstration through the PQ. That is less than 1 in 1 million chance of a non-sterile unit at the end of the validation cycle. This is an expectation from the ISO 17665. So this is a very good international standard that I need to point out. This is really where all of our criteria are coming from, including the accumulated lethality, that is demonstration of an FO greater than 15 minutes. This is calculated using thermocouples throughout the cycle. So it could be that your cycle is 30 minutes at 123 degrees as your autoclave set points. However, you need to demonstrate using thermocouples that you have 15 minutes of lethality at the worst case location within the load. Temperature mapping is not only temperatures within the equipment within the load, but also temperature distribution throughout the autoclave chamber. So we're getting an overview picture of what's happening within the autoclave. Just to reiterate the microbiological performance qualification, the expectation is to use a biological indicator with the organism that's most resistant to steam, which is Geobacillus stereothermophilus. This ISO International Standard 11138 talks about the biological indicator requirements, not only the use of the biological indicator, but probably most importantly, what the manufacturer is doing to produce the biological indicator that meets these specifications. I mentioned something about the equipment load. Here's a summary. During the validation, we should have identified the hardest to sterilize equipment and locations within the equipment. So those hard to sterilize items like long stretches of tubing where it's difficult to remove air, it's difficult for the steam to penetrate. These definitely need to be included in the validation, along with some easier to sterilize items like stainless steel filling parts. These are representative of much of the equipment included in the load. Consistent wrapping and preparation of the equipment, this all needs to be documented. Also, the placement within the autoclave chamber is part of the validation. And again, we're using a combination of biological indicators, chemical indicators, and thermocouples at the worst case location. This is really encompassing all parts of the validation now. A couple photographs here. Usually I would demonstrate this in person, but I included some photos here of biological indicator placement. Specifically, I like this one on the right. This is a long stretch of tubing with a filter assembly and some aseptic fittings here, stainless steel fittings. But the expectation here is to have that thermocouple at the center of the tubing along with the biological indicator. And this is an expectation to show that you're achieving sterility at the worst case location. The draft EU Annex 1 specifically states physical measurement and biological measurement need to be demonstrated during the validation. And here, just a quick shot of an autoclave prepped and ready. All of these locations, the placement of equipment within the chamber is noted during the validation and is part of the routine processing per the protocols. Well, we're getting to the end here. The regulatory expectations, I really am going through this part quick. I feel like I can provide the slides with the references, but I just want to give an overview here. I want to spend some time at the end, just 5 minutes then, to do some show and tell. So the regulatory expectations, I have them listed here. I already mentioned 17665 talks about international requirements for steam sterilization. The ANSI AMI ISO 11135 talks about validation criteria, the requirement to confirm using BIs and thermocouples that your process results in a sterile product. Probably my favorite guidance here is from the FDA. This is FDA guidance for the industry, published in 2004. Take a look at this one. This is not a regulation, but rather a guidebook on how to meet these international regulations. So take a look at FDA guidance for industry for parenteral products in 2004. Air removal verification, this is a hot topic right now. FDA guidance says that air removal needs to be confirmed as part of validation and also as part of your routine monitoring of autoclave performance. The AMI ST79 talks specifically about an air removal device called Bowie-Dick test. Same with the draft EU Annex 1 says that there needs to be adequate assurance of air removal and steam penetration on a frequent basis, and that's using a Bowie-Dick test as well. FDA guidance gives very good requirements for biological indicators and thermocouples. And really, at the end of the day, this slide is giving what I think are the top 8 requirements for a successful validation per current good manufacturing practices. So this maybe is not all written down, but it is definitely the list of 8 factors that will build up a successful validation. Use the biological indicators and thermocouples at reduced worst case parameters in the autoclave, show reproducibility, that you can not only have a sterile product once, but over many times in the initial validation. Could also be periodic time-based validation. Have a documented plan as part of the protocol. Document the results in a report. You'll have a robust validation with a new autoclave or new equipment, but also periodic time-based sterilization validation or change-based validation. If something's happening to improve the autoclave or new equipment into the autoclave load, that requires validation as well. So here I have typically just some slides to talk through these process verification tools, but instead I'll do a little show and tell. First off, biological indicators. We have a few different types. The spore strips you can see here is a blue envelope with a white paper biological indicator where the spores are inoculated in the envelope here. The envelope is just adding protection for the spore strip post sterilization. There's no risk of contamination until the aseptic transfer. Post sterilization, the white strip should be placed into a tube of culture media. So this strip is placed in equipment through the sterilization cycle. Here I have just an example of a stainless steel fitting. I'm not sure if you can see inside, but there is in fact a biological indicator, and the wire here is a thermocouple that's placed adjacent to the thermocouple in the stainless steel fitting. Now that's how you would prepare this part for sterilization. You would have a sterilization wrapping. This is a Tyvek and film bag. The part would go into the bag. Prior to the sterilization, the bag then would be sealed up, and this is a very typical look at a bag with equipment probed and ready to go for your sterilization validation. You have the biological indicator at a worst case location adjacent with a thermocouple. We also have a couple different types of biological indicators. This is a self-contained biological indicator where there's an ampule of the growth media and the small inoculated paper disc. This does not require the aseptic transfer after sterilization. You would remove this from the autoclave cycle, activate by pressing down, and the activation really is just releasing the media to come into contact with the biological indicator. Then this would be incubated on its own and checked for microbial growth. Hopefully the sterilization cycle worked and there's no microbial growth. That has a reduced incubation time of 24 hours, so you could have results ready after 24 hours. We also have what's called a rapid read biological indicator. This is a self-contained version as well. And this has a readout of 20 minutes, so very quick there. Okay, lastly, I just want to talk about a couple chemical indicators, specifically the Bowie-Dick test pack. This is to confirm that you have complete air removal through the pre-vacuum cycle in the autoclave. This pack is placed within the sterilizer in an empty chamber and run with a Bowie-Dick test cycle, a specific cycle to confirm performance of the autoclave. Inside that wrapped pack is a stack of newsprint here to create a worst case challenge for that air removal cycle. And at the center of the pack is a chemical indicator. And if there was successful air removal and steam penetration through that wrapped pack, this chemical indicator would change color to a dark blue. So this is complete removal of the air and steam penetration would result here. If you did not have a successful air removal, you would have air blocking steam from contacting the chemical indicator and incomplete color change in this case. So this happens on a daily basis to confirm performance of that air removal. So I know that was pretty quick demonstration there, but I did want to go over a couple of these sterility assurance products with you. That really brings us to the end where I want to say thank you to the audience for your attention. Also, thank you to ISPE for hosting this for Steris. Also to Neo and Richard, my two colleagues there in Singapore. At this time, let's take some questions. I know that there was some chat going on. I appreciate that. So maybe we can pull up if there are any questions. I'm also okay to take live questions. Okay, let's see the chat box here.
So Aaron, there was a question from Sim saying, during the PQ of Autoclave, how can we ensure that the load pattern we designed reach its optimum performance?
Yes, that's a great question. So really, when you're creating the load pattern, you are monitoring the load, the equipment with your thermocouples and biological indicators. So during the cycle development, placing the thermocouples, biological indicators in some test cycles throughout the load, And that's where you'll demonstrate with the results from the thermocouples, results from the biological indicators, that you have complete steam penetration and microbiological kill. So it's really the use of the thermocouples and the biological indicators.
Okay, thank you. During requalification, is it okay if the temperature of any one thermocouple goes beyond 124 if our operating range is 121.1 to 124?
Yeah, that's a good question. I would say that during the validation with a thermocouple, we really need to define an acceptable range of temperatures. So I think that the best guidance is that the temperature range should be within 121 and 124. If it's going beyond that, there's probably some opportunity to optimize the control of the autoclave. So typically I would say to investigate. It's not necessarily a problem, but it's worth looking into. You'll want to be sure you have good consistent temperature throughout the autoclave, including throughout the equipment. So typically a range of 3 degrees is sufficient.
So Michelle asks, for wrapping, are companies moving away from autoclave tape and heat setting for bags, only using self-sealing bags?
Yes, yeah, absolutely. This is the best way forward. I think that autoclave tape and blue cellulose paper wrapping really lends itself to some problems, as I mentioned. The self-seal bags are very efficient and easy to reproduce. I had this example here is in fact a self-seal bag. So you place the equipment in here and you can expose the adhesive and fold this over, and now the bag is sealed, ready to go in the autoclave. That really is the best method for small equipment like that. Just make sure if you're using a self-seal bag like that, my recommendation is to be sure that it's made of a Tyvek material versus a paper material due to the reduced particle generation and the better microbial barrier properties.
Thank you. Is there any guide for determining the number of thermocouple in some autoclave size? This is from Pitoyo.
Yes, yeah, I would say that there's not very good guidance in the regulations, but my benchmarking experience is that you definitely want to use minimum of 12 thermocouples and 12 biological indicators in each cycle, in each chamber run. However, if you have a very large autoclave, maybe it's large like a walk-in style, then I would even increase that to more than 20 in that case. But your normal autoclave where you're pushing in a cart, typically you've done some cycle development work and you've found the worst case locations. So I think if you're using 12 as a minimum, that's acceptable.
Okay, from Aniruddha. In the pre-vacuum phase, is there a phase time excess alarm? Does it affect SAL?
Yeah. Well, yeah, this is really based on the performance of your autoclave. I would say that the pre-vacuum stage shouldn't take more than 10 or 15 minutes. If you have a very large autoclave, maybe it takes a little bit longer, but the critical parameter here is to achieve a change in pressure during the pre-vacuum, reproducibly, repeatably, maybe 3 or 4 vacuum and steam injections. This should happen in maybe 15 or 20 minutes, but it's that change in pressure from steam injection to that vacuum to ensure that you have the air removal. So if it's taking longer than 15 or 20 minutes, maybe you need to shift that range higher, where you're injecting steam a little bit higher, and then you're not pulling such a deep vacuum, then the equipment can execute that process more quickly. So if it's taking a long time, maybe have the vacuum not so deep, but have the steam injection to a little bit higher pressure.
Thank you. Thank you. From Vinayak, how can we deal with the abrupt temperature drops of 5 to 10 seconds in any single thermocouple out of 24? Can we accept this? What are the probable causes?
Yeah, well, it's hard to say exactly, but I think these drops are typically due to the presence of condensation. So you can imagine if it's saturated steam at 121 degrees, in the presence of condensation, that temperature will drop abruptly to 100 degrees, the boiling point of condensation. So typically these abrupt drops are due to condensation. And I would say to prevent that, you need to think about positioning the equipment in the autoclave such that the condensation will not pool, that it would drain freely, I would say, at those locations. So if you have maybe a bowl, stopper bowl shaped like this, condensation will pool in the bottom, versus if it's on its side, the condensation could drain freely. That's the most common result or cause of those abrupt drops. I would say trapped air in a long stretch of tubing could be a possibility as well, but typically it's condensation, and changing the orientation of the equipment is a solution.
Thank you. So if any of you have any follow-up questions, please unmute and or post it on the chat as well, and we'll follow up. Hoi Uyen asks, how many probes are required in minimum for sterilization validation?
Yeah. Yeah, again, I would say minimum of 12. Again, during the cycle development, you're finding the worst case locations. So a lot of the work happens prior to the validation, where you might use during the cycle development many more than 12, but you're assessing that data and selecting the coldest or hardest to sterilize locations. But I would say minimum of 12. In a large autoclave, probably more like 20.
Okay, so this is a longer one. Is it mandatory or commonly expected to have fixed placement of the load in the autoclave during PQ and routine? Or if we can demonstrate during PQ that the exact placement does not matter, no cold spots, is it okay to have non-fixed placement of loads?
Yes. Yes, this is a great question. I would say that if you have the data to show that the placement does not matter, that you've demonstrated during your validation or demonstrated during your cycle development that the placement is not important, then during routine processing, you do not need to control the placement. The key here is to get the data, do the testing during cycle development, do the testing during validation to show that if the equipment is placed on the top shelf or on the bottom shelf, there's no impact to the temperatures. And if you've done that, then I think you do not need to have fixed placement. So I think that this question really lends itself to gathering the data throughout the cycle development and the validation.
Thanks, Rosalie, for that question. So from Mahendran, he's asking, from your experience, was there ever a time equipment qualification was done within the autoclave with a specified amount of WFI within the equipment? Is it necessary? And if yes, why? The equipment in question is the main body of a glass bioreactors from my previous
Yes, yeah,
site.
that's a good question. And this is a very specific question. I think that typically you do not want to have liquids in a hard good or equipment load. However, I know in some of these bioreactors, sometimes certain types of filters and filter housings need to be sterilized with water, WFI, in the equipment. And of course, we need to protect the equipment. We need to protect filters, things like this. So I would say in these specific instances that water in the equipment is okay. I would say there we have an opportunity then, or a requirement, to demonstrate that the liquid itself is becoming sterilized as well. And for that purpose, there's a different type of biological indicator, a biological indicator ampule. So you would place the biological indicator in the liquid as well and demonstrate sterility there. So I would say for these unique situations like the bioreactors, like the filters, then water in the load sometimes is necessary.
Okay, please keep the questions coming. This one is from Balakrishnan. Like for cleaning validation, we do lab scale studies or clean characterization studies to determine cleaning contact time requirements. Are there any similar studies for sterilization to determine the SIP hold time requirements instead of going by a blanket 1 to 1.1 centigrade for 30 minutes?
Yeah, that's a good question. So I think I'm understanding this correctly. For a steam in place cycle where it's perhaps a product tank that you're connecting to steam rather than a batch autoclave sterilization of equipment, I would say that the requirement is still to have the lethality greater than 15 minutes of FO. A cycle of 121 for 30 minutes should achieve this. Again, it needs to be tested with the biological indicators and the thermocouples during validation. And typically, my experience is that large tanks or equipment that have been steam in place, SIP sterilized, they would be held under pressure during storage. So if the tank is sealed and pressurized, then you are confirming integrity of that and thus sterility of that equipment during the storage. So I would say that if you're monitoring and maintaining a pressure on an SIP system, then it can be held for a specified amount of time, whatever time you choose, provided that the pressure is maintained on the equipment. So hopefully I understood that question right, but please send me a mail or chat if I did not understand the question correctly.
I hope that was okay. Okay, next question from Anla. After sterilization, do we need to demonstrate the hold time of sterilized load? How long can we store the sterilized load in normally?
Yes. Yeah, this is a good question. The FDA guidance for industry that I talked about, the 2004 document, absolutely recommends a clean hold time that's validated. So that's post cleaning prior to sterilization. And it also states a sterile hold time needs to be validated. Now, typically this is done by sterilizing the equipment in the wrapping preparation that you've defined in your validation, storing this for a defined period of time. My benchmarking experience is that 30 days, 4 weeks, or 30 days is probably the maximum. But to validate this, I recommend holding the equipment in the normal wrapping, in the normal storage room or method for that maximum 30 days, and then using that equipment as part of an aseptic process simulation or a media fill to demonstrate that your methods of holding are sufficient to result in filling of a sterile product. So that's my recommendation, is to hold those materials and perform an aseptic process simulation.
You're doing great, Erin. Thank you.
Thanks.
Just a quick advert. If during the next few minutes, we would really appreciate if everyone could just click on the link that Christina has posted. It's just for a survey to help us to get feedback from this session so that we can do more and improve for the future. Please do click on it. You can fill in the survey after the session. It will literally take you a minute, but it means a lot for us. So please do click on that and help us out. Thank you. We have the next question from Sim. Do we perform half cycle method validation for steam sterilizer? Erin, I think you're frozen. Oh, we seem to have lost Erin.
Option. There's really two ways to do this. The half cycle is done basically by, during validation, reducing the exposure temperature by 50%. So if your routine cycle is 123 degrees for 40 minutes, then your validation would be done at the same temperature for 20 minutes. Now that's one way to do it. Another way is to really just use this idea of worst case parameters. So you would reduce the temperature from 123 to maybe 122 during the validation, and the time from 40 minutes to say 35 minutes. So there's really two different ways, the half cycle or the worst case, but it's really up to you to decide how you want to meet that.
Okay, thank you. Another question from Pitoyo. If we have several cycle recipe and several load pattern, is it acceptable if we determine the worst case load pattern and cycle only for the demonstration on PQ?
Yeah, that's exactly the strategy I would use. Again, if you've gathered the data during cycle development and you've analyzed the data and documented that one load pattern or one set of equipment is harder to sterilize than another, and you've done all that work up front, then definitely during the performance qualification, you can rationalize using the worst case equipment. So that's a very good strategy, especially if there's a lot of different loads and a lot of different equipment, then definitely using that worst case strategy is a good way.
Okay, thank you. From Chase, we have a question. Is it okay if minimum loading pattern is replaced to empty pattern during validation? And secondly, can we replace to new material from similar material in validated pattern?
Yeah, this is a hard one with the minimum load. I would say that for whatever reason, my experience is that an empty chamber is different than a minimum load. I don't have a good rationale or a good scientific reason for that, but I feel like regulatory expectation is that a minimum load should have some number of equipment. The load should consist of something being sterilized. So typically what I've recommended is to do, as part of maybe even your operational qualification on the autoclave, to do that temperature distribution mapping in an empty chamber. That's the qualification of the autoclave. And then for the qualification of the load, I think it's still required to have at least one cycle with some minimum number of equipment. Now, the second part was, I think, to rationalize new or different equipment into a validated loading pattern. I don't think that you always have to perform the validation on a new equipment or a changed equipment, provided you've taken a look at the change and assessed, is this a risk to my validated load? Is this a risk to this sterilization process? So if you've assessed it and documented that it's not a risk based on the significance of the change, then I do not always think that there needs to be a validation. Now, it might be a good idea if you're doing time-based validation, then to include that new item in the next annual qualification, for example. But definitely assess it, have your sterility assurance experts evaluate and document their assessment.
Thank you. From Mala, the question is it necessary to validate the steam quality during PQ?
Yes, yeah. There's an expectation to confirm the steam quality. Typically, this is done not just during the qualification, but on a routine basis. I think even on a quarterly basis. I'll have to check the regulations, but I think that there's a requirement as frequently as quarterly to check the steam supply. So typically, there's a port on the steam header where the autoclave connects, a point of use check, and there are quality assurance tests to be done on the steam quality. So I think it's a good idea to do it as part of PQ, but I think definitely it's an expectation to do this on a routine frequency.
Thank you. Now, from Vinayak, the question is, can temperature gradient and millivolts signals traveling through thermocouple having higher temp gradient cause errors in temp readings?
Yeah, this is really a question about the mechanics of the thermocouples. I don't know for certain, but I think that there's probably fairly low risk that that would impact your sterilization validation. I would say if you're using some of the proven equipment out there, like the K validator and thermocouples, or there's companies like L Lab that has remote temperature sensors, and if these equipment and data loggers are calibrated and you've shown reproducible results through your validation, I think there's probably pretty low risk. I have to say that I don't know, I'm not an expert on these temperature monitoring devices. I would say talk to an engineer from one of these companies and see what they have to say. I think that they're proven out and there's low risk, but if there's a concern, maybe talk with the engineers.
Okay, from Nan Nguyen Trong, we have many load patterns for sterilization. Some loads have the same equipment parts and placement. The only difference is the number of equipment parts. Can we only validation the maximum load and using that data for minimum loads too?
Yeah, I would say that during the initial validation, use the bracketing approach where you evaluate the maximum number and placement and then also the minimum number and gather that data and keep that in the file. Then I would say that if you've demonstrated that they're equivalent or maybe maximum load is worst case, then during your routine qualification, I don't think it's a requirement to do the maximum and minimum, but then you could concentrate on just the maximum. But again, it's always safest to run that one extra study and have that information in your validation file for the minimum load.
Okay, just a follow-up question from Anla. I want to come back to the question regarding the hold time of sterilized load. We can validate in media fill process, or we should perform a separated study for verifying hold time of storing. How long should we perform revalidation for autoclave? I
Yeah.
mean the temperature distribution and penetration.
Yes, yeah, this is good. I'm glad that you asked the follow-up questions here. So for the hold time study after sterilization, I think my opinion here is that there's benchmarking that shows that the aseptic processing simulation is sufficient, provided that you have a reproducible sterilization wrapping, you have microbial barrier data on the sterilization wrapping, that you have an integrally closed wrapping. So if you're using a sterilization pouch like I showed, that the seals are integral. So there are some other evaluations that probably can help minimize the risk of all of that. And you should ask your sterilization wrapping provider if they have that type of information. So for example, Steris manufactures and provides sterilization wrapping systems, and we could help you develop a rationale with all of that different data to have a robust validation of your sterile hold times. So that would be the best way to have confidence in that sterile hold time. So secondly, with regards to the revalidation, I would say the time-based frequency should be no longer than 1 year in between performing the heat penetration and biological indicator testing. However, if there are ever changes to the autoclave or to the loading pattern, these changes need to be evaluated for their impact to the validation. All of that change control should be documented and the rationale should be documented. Otherwise, the change does result in a validation. So it's time-based and change-based.
Okay, so we've got 2 final questions.
Great.
If anyone wants to continue posting questions, please do so, and we'll forward them on, and then we'll get response to you. Also, please click on the link to help us with your survey feedback. From Rosalie, the question is it always a requirement to do minimum 3 runs for PQ for each autoclave unit? If, for example, I have a few autoclave units of same make and model, can I do 3 runs on one and the rest 1 run each?
Yeah, this is great. I would say, once again, gather the data and do the analysis. I would say that if you have data on the same loading pattern in 3 identical autoclaves, 1 run, and you can demonstrate some sort of functional equivalency across these 3 autoclaves, and you have that data and that analysis, then I think it's perfectly acceptable to do the triplicate or 3 runs in just one of those autoclaves. If you have the data, if you've looked at the data, if you've documented the rationale, then I think that's a great approach.
Great, thank you. So final minute. If a sterilization cycle designed independent of load size, then can we consider only maximum load as worst case and skip the minimum load pattern from validation study?
Yeah, I see a common theme here. I think with this one, again, somehow we have to have the data in our validation file for the minimum load. However, I don't necessarily think that on your time-based frequency for requalification or revalidation that you need to do the minimum load every year, provided that you have that data in the file. So maximum load is typically considered to be worst case, but we do need to have the data for the minimum load as well.
Okay, brilliant. Okay, brilliant. Thank you, Erin. That was a lot of questions over quite a short period. Thank you all for your questions and for your attention this evening, afternoon or morning, depending on where you are. Thank you, Erin, for all the time that you spent preparing and for joining us this evening. If anyone has any other comments, please post it in the link. There will also be follow-up emails with the presentation and a recording of this session. So you will be able to access it should be later this week once we've got the link sorted out. So thank you all very much for joining us. Erin, we wish you a fantastic day ahead.
Yes. Yes, thank you everyone, and Linda, Christina, Neo, Richard, thank you for this opportunity. Be well, talk to you soon.
Thank you very much.